Merhaba arkadaşlar, hoş geldiniz. Kaldığımız yerden devam edeceğiz. Ee, Geçen ders bu teoremi vermiştik. Ordinary bir point etrafında çözümün işte analitik fonksiyonlarsa P, Q, R çözümün varlığı ve çözümünde bir analitik fonksiyon olduğu. Y1 ve Y2 iki tane linearly independent çözüm var. Bunların arbitrary combination'ı linear combination'ı ve bu iki fonksiyonun da radius of convergence'ı analitik fonksiyonların e, Q bölü P ile R bölü P analitik fonksiyonlarının x0'daki açılımlarının e, yarıçaplarının minimumu kadar en az oluyor. Dolayısıyla da hani bunlar analitik fonksiyonlarsa y1, y2'de analitik fonksiyonlar olacaklar. X0 etrafındaki bir açık kümede. Peki şimdi bir örnek yapalım. Let's do an example. So solve the equation, Airy's equation. Airy's equation. What is this? Y double prime minus x times y equals 0 for x. Okay. So if you compare this with the general form we have discussed above, px is just 1, qx is 0, the coefficient of y prime, and rx is equal to minus x. And you see q bölü p is just again 0, and r bölü p is again minus x. R analytic functions everywhere with radius of convergence at any point infinite. So theorem guarantees that there exists a power series solution, general solution, and the y1 and y2, the two linearly independent solutions, are also analytic functions with the radius of convergence infinite. Okay, so by the theorem the general solution has the form y equals an x to the power n from 0 to infinity, and this can be written as a0 y1x plus a1 y2x, where yix are analytic functions with radius of convergence infinite. Okay, so let's find the solution. How can we find this? Well, here is the function y. Well, what is its derivative? I'll just plug this into the equation. So for that, I need to take the derivative. So this is n times a n x to the power n. This is of course equal to what? Since n equals 0 is 0, so this becomes 0, I may just start from n equals 1. So this is a n times a n times n minus 1, x to the power n minus 1. And similarly, the second derivative will be, you take the derivative again. So n times n minus 1, a n x to the power n minus 2. I start from 1 to infinity, but again, when you plug 1, you get already 0, so we may just start from 2. Okay, now let's plug them into the equation. Equation to get, okay. So y double prime is this minus x times y. So this one, and this is 0. Okay, so this is just and from 2 to infinity n times n minus 1 a n x to the power n minus 2 minus n from 0 to infinity a n x to the power n plus 1. Right? These are two analytic functions given by power series expansion. You just multiply them as if you are multiplying polynomials. So this x comes in and it makes a n times x to the power n, a n times x to the power n plus 1. Alright, now next thing we want to do is to combine these two summations into a single summation. But you see the exponents of x are different. First I have to equate them. How can I do this? Alright, let me make this n. So I can make it n by just replacing n with n plus 2. So instead of n, I write n plus 2. N becomes n plus 2. N minus 1 becomes n plus 1. A n plus 2. And here I have xn. Since I increase this n by 2 to get equal summation, I should start with n equals 0. Right? You see, when you plug 0, you get 2 times x to the power 0, and when you plug 2 here, you get 2 a2 times x to the power 0, so you get the same thing. And here, let's make this n. So I replace n by n minus 1. So I have this. Since I replace n by n minus 1, this will start not from 0, but it should start from 1, right? So for n equals 1, you have a0 x. When you plug n0 here, you get a0 times x. So you get the same thing. Now I can combine these two. But here the 0 term is, doesn't exist here. So I just leave it outside. So for n equals 0, I have just 2 times 1 times a2 x to the power 0 plus the summation from 1 to infinity n plus 2 n plus 1 a n plus 2 x to the power n minus n from 1 to infinity a n minus 1 x to the power n 0. Now I can combine the two. So I have 2a2 here plus from 1 to infinity and then I have this term n plus 2, n plus 1, an plus 2 minus an minus 1 times x to the power n minus 1, and that's 0. 0 can be thought as the zero power series, right, where all the coefficients are 0. And we know that if two series are the same, then the coefficients of x to the powers n must be the same. Here the constant term, right, is 2a2. Here the constant term is 0. And the exponent of x and x squared and so on, x to the power n, is this term, n plus 2 times n plus 1, an plus 2 minus an minus 1, and here that coefficient is just 0. So from this we get what? Well, we see that a2 must be 0, and then an plus 2 is just an minus 1 divided by n plus 1 times n plus 2. And this is true for n larger than 1, right? For n larger than 1. Okay, so I have this. Now from this recursion formula, I can just, compute all the coefficients. Okay, so for n equals 1, I get a3, and when you plug 1, you get a2 divided by something, but so when you plug, no, okay, when you plug n equals 1, sorry, I get a0 here, and then you plug n equals 1, so you get 2 times 3, so it is 6. And then a4 is what? A4 is just, so n equals 2. When n equals 2, you have a1 over n equals 2, so you get 3 times 4, which is 12. What about a5? So n equals 3. When n equals 3, I have a2 here divided by something, but this is 0 since a2 is 0. And so on. Let's compute a couple more. A6, so n equals 4. So this is just a3 over n equals 4, so 5 times 6. But a3 is already this, so it is a0 divided by 5 times 6 times 6. Okay. And what is a7? A7 is n equals 5, right? N equals 5. So you have a4. I put 5 here, so it is 6 times 7. And what is a4? A4 is just a1 times, sorry. Okay. A4 is just a1 times 12. So 6 times 7 times 12. And so on. Okay. One can compute all the series. So what is this gadget then? at least couple of terms. So this is a0 plus a1x plus a2x square, and so on. Now let's plug all these. So I have a0 plus a1x plus a2. a2 is just 0, so there is no a2. And then I have a3, which is a0 over 6 and then x cube, and then a4, so a1 over 12 x to the 4 plus x5, a5 is 0, so no x to the power 5. A6 is just a0 over 180 x to the power 6, right? And then uh, a1 over 42 times 12 x to the power 7, and so on. And you see here I can write this as in a0 parentheses, this is 1 plus x cubed over 6 x to the power 6 over 180, and so on, plus in a1 parentheses I have x plus x to the power 4 over 12 plus x to the power 7 over 42 times 12. Okay, so this is my y1, and this is my y2x, and we know that they have radius of convergence infinite by the theorem, right? Theorem tells us that. Okay. Okay. Let me do one more example. So here we had one example. Here is another one. Okay. All right. Y double prime minus x times y prime plus 2y equals 0. Let's find the general solution again. Okay, this is equal to what? So here, if I compare this with the general form, then px is just the constant function 1, qx is minus x, and rx is equal to 2. Alright, so q over p is minus x, and r over p is just 2. These are again analytic with radius of convergence infinite. Therefore, solution general solution will be just a0 times y1, a1 times y2 by the theorem, and the radius of convergence again will be infinite. Okay. Let's find the solution. So I start with this. Okay, what is y prime? Uh, so y prime is just n from 1 to infinity n times a n x to the power n minus 1, and second derivative is just from 2 to infinity n times n minus 1 a n x to the power n minus 2. Plug them into the equation. What was the equation? So y double prime minus x times y plus 2y equals 0, right? Yes. So we get what? N from 2 to infinity n times n minus 1 times a n x to the power n minus 2 minus x times 1 to infinity n times x to the power n minus 1 and plus 2 times y. Here I have to be careful. Yes, n times a n times x to the power n minus 1 and 2 times a n times x to the power n, and they all add up to 0. Okay, so let's equate the uh, powers of 2. So let's make this n. To make it n, I increase the index by 2. Okay. Since I increase this index by 2, I have to decrease the point where it starts by 2. What about this one? This is n times a n times x comes in and it becomes x to the power n. And then I have 2an x to the power n from 0 to infinity. And everything adds up to 0. Okay, now all the powers are equal, x to the power n. So I can write this as a single summation. But you see, I have two extra terms here. Here this starts from 1, but these are starting from 0. So I have to take out the terms corresponding to n equals 0 outside the summation. So when I plug 0 here, I just get 2 times 1 times a2 x to the power 0. And from this one, when n equals 2, I get 2 a0 x to the power 0 plus the rest are from n equals 1. So from 1 to infinity. And what is the coefficient here? It is just n plus 2, n plus 1, a n plus 2. What is the coefficient here? Minus n times a n and here just 2an, and x to the power n, and everything adds up to 0. Alright. I have a power series. This is the constant term, namely 2a2 plus 2a0 plus, and then I have this summation term equals 0, right? This thing here. Well, since this is the 0 summation, the coefficients of this power series must be all 0. The coefficient of the x to the power 0 term, so the constant term, is just 2a2 plus 2a0 equals 0, which gives us that a2 is equal to minus a0, right? And I have this term, which is n plus 2 times n plus 1 an plus 2 minus, or plus 2 minus n an equals 0, right? 2 minus n. And this is true for n larger than or equal to 1. And from this we get an plus 2 is just, I take this to the other side, so I have n minus 2 times an divided by n plus 2 times n minus n plus 1. Yeah. For n equals larger than 1. Now I can compute all the coefficients. A2 is minus A0. And from this, if I plug n equals 1, I get A3. A3 is what? I plug 1. So I get minus A, n equals 1, A1, divided by n equals 1. So you get 3 times 2, 6. Alright, what about A4? A4 is just, so n equals 2. When n equals 2, you just get 0 here. And then A5, so n equals 3. When n equals 3, you get 1 times A3, and then n equals 3, so you get 5 times 4. Yes. A6, n equals 4, so you get 2 times A4, but A4 is 0, so this is just 0. And let me compute one more. A7, n equals 5. When n equals 5, you just get 3A 5 divided by n equals 5, so you get 7 times 6. Alright, so let's write down the solution then. It's the power series an times x to the power n. So it is a0 plus a1x plus a2x squared, and so on. Let's see what we get. A0, a1x, and then a2. A2 is, I guess it was 0. No, a2 is equal to minus a0. So minus, sorry, a0 x squared plus a3. A3 is this, minus a1 over 6x cubed. A4 was 0 because it corresponds n equals 2. When you plug 2 here, you get 0. So there is no x to the power 4 term, and then x to the power 5 term. So A3 uh, over 20, but A3 was minus A1, so minus A1 over 6 times 20, which is 120, and x to the power 5. No x to the power 6 term, x to the power 7, so 3A5. A5 is just this gadget. Yes, so it is minus 3A5. A5 is this, A1 over 120 times 42 x to the power 7, and so on. Okay, and you see this can be written as what? In A0 parenthesis 1 minus x squared, and then well, there is no other A0. Yes, and then there are A1 terms, x minus x cubed over 6 minus x to the 5 over 120 minus, okay, uh, x to the power 7, so 3 and this is cancelled, so 40 times 42, and so on. So even power terms are only these two, the others will be 0, because since A4 is 0, A6 is 0, this will imply that A8 is 0, and so on. So this is what we get. So this is my y1x, and this thing is y2x. All right. Okay. Uh, okay. Now we may consider a new subject. Okay. So-called regular singular points. As I said last time, singular points are very important, although they are not, common. I mean, most of the points are regular. Only couple of them are singular, but you cannot just avoid them because they tell us, behavior of the solution at some, you know, important situations, so you cannot just avoid them. So in practice, in engineering, in science, singular points occur, and one has to understand them. Okay, well, consider again this differential equation. And suppose x0 is a suppose x0 is a singular point. In other words, p of x0 is equal to 0. All right. In general, solution about such a point is very difficult to obtain. So in general uh, obtaining uh, the solution about a singular point uh, is quite difficult. However, uh, in some cases, uh, we may obtain the solutions. Okay, now what's that uh, case where we can obtain a solution? One of them is so-called regular singular points. A singular point x0 for the equation above equation is called uh, a regular singular point if what happens if the following limits exist. If the following limits exist. What are they? One of them is this: limit as x goes to x0, x minus x0 times qx over px and limit as x goes to x0. This time I have x minus x0 squared rx divided by px. Okay, so if this limit exists, both of them, then we say that this point x0 is a regular singular point. So it is singular, but it is not, too bad. It is still some, mild singularity. It's a regular singularity. Okay. Example. One example is the following. 1 minus x squared y double prime minus 2xy prime plus 2y equals 0. So px is 1 minus x squared, qx is minus 2x, and rx is the constant function too. All right. Well, singular points are the points where the coefficient of y double prime, which is p, is 0. So if I equate this to 0, I get 1 minus x squared is 0. And from this we see that x is plus minus 1. So these are the only singular points of the equation. Okay? All other points are ordinary, and life is easy, kind of, right? Okay, let's check whether they are regular singular points. Okay. Let's see if they are regular. Are they regular? Well, let's start with the first one. Okay, let me say x0 minus 1. So I have to check the two limits. Limit as x goes to x0, x minus x0, qx over px. So what is this limit? As x goes to minus 1, x minus minus 1, so it is plus 1. Okay. And then qx. What is qx? Minus 2 times x over px, 1 minus x squared. Well, what is this limit? As x goes to minus 1, so x plus 1s are cancelled, so I have minus 2x, and then I will have my 1 minus x, and if I plug minus 1, so we get 2 here, and another 2 here, which is 1, and this limit exists. What about this one? X minus x0 squared Rx divided by Px. So limit as x goes to minus 1 again, x minus 1 minus minus 1, so x plus 1 squared. Rx was 2, okay, 2, and then 1 minus x squared. Yes. So again, x plus 1, one of them is cancelled. So x plus 1, and then I have 2. X plus 1 is gone, so I have just x minus 1. And when you plug x equals minus 1, well, you just get 0, which is again, uh, you know, so this limit also exists. Hence, x0 equals minus 1 is a regular singular point. So it is singular, but it is not too bad. Okay. What about the other one? X0 equals 1. Well, again, we have to check the limits. Limit as x goes to x0, x minus x0. Okay. And then I have qx over px. So limit as x goes to 1. I have x minus 1. Q was minus 2x, I guess, and this is 1 minus x squared. Let me check. Q was minus 2x, yes. Okay, now here x minus 1 is gone. Okay, let me maybe more careful. So minus 2x. X minus 1 is cancelled with 1 minus x. So 1 plus x is left. But this is x minus 1, and here I have 1 minus x, so there's a minus sign. So we have this, and when you plug 1, you get 2 over 2, which is 1. So this limit exists. What about the other limit? Limit as x goes to x0, x minus x0 squared, rx divided by px. So this is just as x goes to 1, x minus 1 squared. R was, let's see, R is 2, 2 over 1 minus x squared. Yok. 1 minus x squared. Değil mi? P oydu. One minus x squared. Okay. All right. So this is limit as x goes to 1. X minus 1 and x minus 1 are cancelled. So I have minus, okay, so here I have x plus 1. And since there's minus sign, because this is x minus 1, this is 1 minus x squared. Wait a minute. No. One of the x minus 1 is gone, so I have x minus 1. And here I have 1 x plus 1. Yeah, so I have this, but x is going to 1, so this is just 0. Again, hence, again, x0 equals 1 is a regular singular point. All right, so let's see. Okay. So next time we will see the form of the solutions about regular singular points. But before that, we will consider so-called Euler's equations. We will see how the solutions look like and so on. So they are special kinds of equations where we have regular singularities, but they are kind of easy. We can find the solutions easily, and then they will just actually show us how the solutions look like in general. Okay, so let's stop for today.